What's up, everybody? Hey, before we start this video, make sure you read your email from your teacher. You're supposed to go to student.desmos.com and do the Desmos activity first. Get that guy done, and then come back to this video, and we'll get started. Well, now that we're done with the Desmos, I walked around for the kids who were in class and kind of saw that we're still a little shaky on the purple note card. That's what that whole Desmos was about, was seeing if you could tell how things affect with the purple note card and explaining things. We'll get better at it. So what we got here is our basic, generic, plain old exponential function with all the sprinkles added to it. So here's your base in that case, but you got an a value, an h value, and a k value. And we're not even going to do all 4 steps to the purple note card. We're just going to do the first 2 steps, because the other ones, the dilating and stuff like that, it's so hard to see what happens to an exponential graph. So one of the questions on the Desmos asked you, like, where was the horizontal asymptote every time? Well, it's always going to be at y equals k, because what does k do, guys? What does k do to that thing? Translates up or down in this case. So let's rock and roll with all of this. So this guy right here, he is what? Exponential growth or exponential decay? Let Megan Trainor help you. Exponential growth. It's all about that base, and that base is bigger than 1. So that's our first 2 reasons right here. Exponential growth, the base is bigger than 1. And now what we have to do, there's one more little thing before we get started that is a lifesaver. And I got to take it back to maybe 2018. I'm pretty sure it was not in 2019, but I could be wrong. I don't follow these songs very closely, but we need another goofy little song to help us out. It's not about Megan Trainor this time. But what we want, before we do the purple note card on this to see what this graph looks like, is let's go right here and we make ourselves what I call the, you ready for this? It was the most annoying song of probably 2018. I'm guessing that's when it came out. Do you know what song that is? Baby Sketch. Oh, Shark, excuse me. When did that come out? Baby Shark? I don't know. But we're going to make a baby sketch of this guy. Would you believe that exponential growth, boom, looks like that normally? That is a normal exponential growth. And if you make the baby sketch, that will save your life, as you will see as we come up. So this is what it looks like if it was plain Jane vanilla. But he's not plain Jane vanilla. They added and subtracted and sometimes will multiply some stuff. So the first thing is if they reflect over the x-axis. And my friends, it's about the a value. The a value is the number in front of the base. If he is negative, would you believe that the number in front of the base is an uno in this case? It's just a 1 right there. You don't see him. If he is negative, this guy gets reflected over the x-axis. Does this guy get reflected over the x-axis? No, it does not, so we'll do. But let's pretend he did. If I pretend that he did, would you believe that this graph right here, boom, does one of those right there? It would totally look like that. But that's not happening, so I'm not going to put that on my baby sketch in that case. Then the translation part, we rock and roll that. Translated where? 3 units left, because it's opposite of this guy. And where else? 5 down. Questions about those, right? If it gets reflected or not. But then we've got to do where the critical point was. So don't draw this, but if we were doing a parabola, like old school parabola, would you believe that the parent parabola has a critical point at 0, 0 in that case? Well, that's not the idea for the exponential guy. His critical point is at 0, 1. So quite possibly, guys, there are 2 things that could happen to 0, 1. Because you watch here, 0, 1 is like right there as opposed to 0, 0. And would you believe if you reflected over the x-axis, that 0, 1, bada boom, moves down here. It has somewhere to go because 0, 0 never moved anywhere when you reflected him over the x-axis because he's on the x-axis. So it depends on what we've got going on. However many things that happen in our 2 steps for our purple note card, that's how many things we got to do to 0, 1. So since this guy did not get reflected over the x-axis, 0, 1 is still going to stay at 0, 1. But now we got to translate him 3 units left and, 3 units left and 5 units down. And you just do arithmetic on this. You take the 0, which is where he originally started, and add -3 to it. Where would that turn out to be? -3. And you take the 1 and you add -5, or if you want to think subtract 5, whatever your brain is more comfortable with. Where would 1 move to if you moved him 5 units down? -4. So the critical point of 0, 1, since it's been moved 3 units left and 5 units down, will now be at -3, -4. But before we even sketch that and put that on our graph, we need to know where the horizontal asymptote is. He is the secret to our success. He will always be at y equals k. So where is our horizontal asymptote at? Y equals -5. This thing has been shifted 5 units down in that case. So that's how we'll start. We will start by drawing the horizontal asymptote. Make him as a dashed line. And put that little HA, y equals -5. Now, if I'm going too fast for you, you can always pause the video, but get that guy drawn in there. Now that we got the asymptote there, let's go plot our critical point of -3, 1, 2, 3, -4. And you don't even need to label him. Since we are on a grid, you know, it's like, and we're counting by ones, we know where -3, -4 is. If it was a freehand sketch, you'd have to put that ordered pair there. But then back to our baby sketch. It magically moved over here. Sorry, but my baby sketch, we're going to make him look just like this. This is an exponential growth, so it's going to go bada boom. Pretty basic in that case. We're just doing a sketch. We don't need any other points of this guy. So just a sketch in that case. Do the domain and the range for me, and then check with mine. Domain from left to right, still -infinity to positive infinity. We usually call it all reals. But the range, how low does this go, guys? How low? To -5, but can it touch it? It's not included because there's an asymptote there, and then right here, all the way up to infinity. And this was what I was looking at that very last question on the Desmos for. It's how I know we don't really get that purple note card thing yet. It was the last question on Desmos. Please describe what has happened from this one to this one. That is the sentence that they pull out in college algebra all the time. That's why we keep practicing the sentence. So we got to say the graph of, and then we got to list the parent function, and I need your help. Who is the parent function? If you strip away all the flavorings, all the chocolate, all the sprinkles from this ice cream and strip it down to vanilla, who is the parent function of this guy? It'll be y equals, what do you think? Strip away everything. It's got to be exponential. The x has to still be up in the exponent, but get rid of all of the crap that happened to it. What do you think? Y equals 2 to the x. Right? Y equals 2 to the x has been. The graph of y equals 2 to the x has been. You get rid of all the translations, all the dilations, all the reflections, and my friends, you're left with y equals base to the x. It's all about that base. You know, the base was 2 in this guy. So that's as plain Jane as that graph could get if we stripped him down to vanilla. But they did some fancy stuff to it. They shifted it 3 units left and 5 units down, so it looks a little fancier in that case. So it's y equals base to the x is the parent function every time. It's all about that base. Coolio with this guy. It's a pretty simple day today, right? It's just doing the purple note card again, which, yes, you can use your purple note card, but we're only doing 2 steps. So let's do it again. Megan Trainor needs to help us. Who is the base of this exponential function, my friends? 2/5. Boom, which means that is exponential decay. And we can explain by saying in English that the base is between 0 and 1, but we'll write it in math like so. And this is where we need to go to the baby sketch, right? The baby sketch is going to help us. Let's sketch a basic exponential decay. You help me. Is it the blue one or is it the red one right here? Which one is the exponential decay? Red one, right? So let's make a little sketch of that red guy. This is what he looks like when we strip him down to vanilla. This is the basic exponential decay. Cool? Well, all right, it's time. Step 1, has this guy been reflected over the x-axis? What do you think? Yes. So we'll write it like so. And you need your eyes to help you. Go to the baby sketch and reflect that over the x-axis. Do one of these. Do you feel comfortable that that blue thing is what that would look like if you reflect him over the x-axis? Trust me, that is the most important thing. I've been doing this a long time, and we will never get the sketch wrong if we do that one move. Translate. Where has he been translated? Good. And now, however many things happen here, that's what has to happen to 0, 1. 0, 1 is normally right here. Where would he move to if we reflect him over the x-axis? It would go right here. Where is that? 0, negative 1 is what happens in phase 1. This guy got reflected over the x-axis. And now, this is the point, if my pen would work, sorry, that gets translated 4 units right and 2 units up. So we have to do the translation arithmetic to this guy, right, 0, 1. So let's add 4 to this, and that would go to 4. And then add 2 to this, and where would that put us at? At 1. Negative 1 plus 2 more is 1. Are we okay with that? So that thing had 2 things happen to it. It got reflected over the x-axis, boom, and then it got translated. And remember, that didn't happen back to the parabola because the parabola's critical point was at 0, 0. So that's new. And then the horizontal asymptote will always be at y equals k. So it'll be at y equals 2. Start there. That's how you start your graph. Graph the horizontal asymptote. Don't forget to put the little HA, y equals 2. And if you need to pause, go ahead. Now let's plot the critical point. The critical point is now at 4, 1. So 1, 2, 3, 4, 1. Whoa, whoa, whoa. That is underneath the asymptote. Is that supposed to happen? What do you guys think? Why did that happen? Because it got reflected over the old x-axis. So now everything's down here. And now the question is, how should this guy go? Should it go like this, or should it go like this? Sorry, I missed a little bit there. But which one do you think, the purple one or the red one? Purple or red? What do you think? Would you believe that it's kind of tough to tell if you were just guessing? But if you go back to the baby sketch will show you which one it's supposed to look like. Is it supposed to look like the purple one or the red one? It's supposed to look like this red one right here, just like this. Sorry, I thought I had purple and purple not matching up there, but still, it's supposed to look like this guy. So we'll graph the red guy and do our domain and our range. Yeah. It has been brought up that my baby sketch was wrong. We originally had the correct baby sketch, which should look like this, and now shouldn't the baby sketch look like that? So to go back to where we were, we had a horizontal asymptote at y equals 2 up here, and our point of 4, 1, it should go like this, correct? Thank you for pointing that out. New slideshow this year. Sometimes I go a little too fast and make mistakes, so I appreciate that being pointed out. So let me make a better sketch of this while you guys do the domain, range, and see if you can write your sentence. All right, I got a better picture of it now. What's the range, though? How low does this guy go? Negative infinity, and then the height goes all the way up to our asymptote of 2 in that case, and it's not included because you can't touch it. Then let's strip this guy down to the parent function. It's y equals base to the x, right? So this would be y equals what to the x? 2/5. Right, y equals 2/5. The graph of y equals 2/5 to the x has been, so when I go to the next slide, it's going to have the wrong picture again. So sorry about that, but it does have the right sentence. The graph of y equals 2/5 to the x has been reflected over the x-axis and translated 4 units right and 2 units up. So pay no attention to that because I made another mistake. But this is the right sentence. All right. Let's keep on keeping on. This guy, woo, exponential growth or exponential decay? You decide. I'm going to pause. You decide, and then we'll come. It's a good question if it's growth or decay because it depends on who the base is. What number is the base in this problem? Is it 5 or is it -5? What do you think? It has to be 5 because we learned last class period, which was still new to us, that if it's exponential, the base is either bigger than 1 or between 0 and 1. Right? So you can't have a negative base. Guess what this thing does to the base of 5, though? It does what? Reflects it over the x-axis. So you strip all that stuff away. This is definitely an exponential growth because the base is bigger than 1. Let's make a baby sketch. Meow, meow. So exponential growth like so. And then we'll do our 2 steps. We have already discussed that it has been reflected over the x-axis. I think that we should go to our baby sketch and do that. So that's nice. And then he has been translated just 2 units right, nowhere up or down. Please move the point 0, 1. 2 things happen to this, so 2 things need to happen to 0, 1. However many we fill out, that's how many things happen to it. The cool thing is, if it gets reflected over the x-axis, 0, 1 always goes to the same spot. It always goes to 0, negative 1. That would be, if that happens, because it's the only one place it can move, to right there. But then you do the addition to this. So 2, negative 1. How do you feel about figuring out where that critical point has moved to? And then I will make the most honest mistake ever. I'm going to get the asymptote wrong. See if you can tell what's wrong about it. That is not the correct horizontal asymptote. What is it supposed to be? Y equals 0. But where did I get the negative 1 from? Where this thing like finally ended up at, you know. So just watch out. It's not a negative 1. It's at a 0. So let's graph him. Get my asymptote first. Boom. And plot the critical point and make a sketch. Let the baby sketch help you. Again, pause if you need to. We'll plot 2, negative 1. That's under the asymptote again, which is supposed to happen because it got reflected over the x-axis. And then use your baby sketch for a guide, and I have the correct baby sketch this time. So it's supposed to look just like this guy, but go through that critical point. And then the domain, the range, and the sentence. Cool. So domain, all reals. The range, it went down from negative infinity all the way up to 0. And then if you strip this guy down, would you believe that the parent function is y equals 5 to the x, right? So the graph of y equals 5 to the x has been, blah, whatever your 2 steps say, reflected over the x-axis and translated 2 units up. So that was tricky just because people think that that might be exponential decay. They're like, well, that base is less than 1. That base is not less than 1. It is 5. Right? So it's got to be positive. Cool. Hey, next one, all you, baby. You and a partner, or if you're working at home, get her done. There we go. Sorry I went a little fast, but hope you could get that done. It has not been reflected over the x-axis, so it's pretty basic. It just takes a little bit of understanding. And that's what these first 2 lessons have been, some basic understanding of exponential graphs. What we're going to do the rest of the chapter is get a lot of story problems in, some real-life scenarios. So let's start with 3 plain Jane basic story problems. And I hope next time, I put a lot of time and effort into making a nice little lesson for you. I hope you like it next time, but we'll see how it goes. But this is real plain Jane. So you got either exponential growth or exponential decay, and this is the most generic formula. I would like you to notice the 2 formulas are identical, except for these spots. What is the one little difference between those 2 formulas? This one is a plus, and this one has a minus in it. Let's understand what the letters stand for. A, I just call it some sort of amount after time has passed. Like you get an amount of money or an amount of whatever the heck you're talking about. P, I call it principal. We're going to do a lot of money problems next class period. So principal is the initial starting amount. It doesn't have to be money, though. It's just whatever. And then R is some sort of rate, and T is the time in periods. We're back. All right, so T was the time in periods. So let's check this out. We're going to answer the questions as we go along. Just read this story real quick and find a juicy word. We want to see if it's exponential growth or exponential decay. Find a juicy word. Got a vote? What do you guys feel? The juicy word is? Very easy. That's one of the easiest juicy words. But how do you know it's growing at an exponential rate? It's because it's growing by some sort of percent. That's something that math teachers don't explain fully. It's like there's lots of types of growth. There's linear growth, there's quadratic growth, but if it's growing by some sort of percent, that's going to be an exponential situation. Cool? So up here, we could tell the difference between these formulas, because let's talk about that rate for a second. The rate is some sort of decimal that they give us right here, but why will this always turn out to be exponential growth if we take this decimal and add 1 to it? Let Megan Trainor help you of why that's always going to be exponential growth. Thank you. The base is bigger than 1. And what would happen if you had the rate and took 1 minus it? Would that base always be between 0 and 1? Right? So that's an exponential decay situation. So this guy is exponential growth. They ask us to do part B, write a boop, 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 general equation for the situation. So it's going to start with the A equals for some sort of amount. P is the initial starting amount. They're talking about teen spending in this problem. So you tell me, what was the initial amount of teen spending? Now, not like initially, like at the very first time, but according to the data they have given us, where are they starting from? 2019, right? And what was the teen spending in there? $129 billion. Well, we don't need all the zeros. We'll just put the 129 because we'll just know that our answer is in billions later, right? And then because it's exponential growth, we're going to take this percent and change him to a decimal. Remember, you move him 2 places to the left. So that would be like 0.035. But guess what has to happen to him? We have to add 1 to him right away. So why don't we just call that 1.035? All good with that? But then we're going to raise it to the teeth power. No, not teeth, but to the t power. Why to the teeth power? People are like, why don't you do like to the 6th power? Why don't you do it to the 6th power? Because we're going to do 6 years in here, because they say write the general equation. So you've got to have the t and the a in this guy. Okay? Growth or decay factor, that's always this number. Boom! Whatever number you got right here, that's the answer to part C. This is a growth, so our growth factor is 1.035. It is growing more than 100%. Now here's what I'd like to ask before we get going. Is it going to grow really, really fast or really, really slow? It's growing, right? But what do you think about that graph? You played with it on the Desmos. Will that base of 1.035 make the graph grow really, really fast or really, really slow? Good. It is going to grow really, really slow, because when that base is close to 1, it almost turns out to be like a flat horizontal line. If it was a doubling factor, that thing goes boom, it does one of these, and if it triples, it grows really fast. When it's a growth, the further away that guy is from 1, the bigger he is, the faster it's going to grow. This is going to grow really, really, really slow. 1.035 is very, very close to the number 1. So what we'll do on part D is answer the question. So estimate teen spending in 2025. I'd like you to show me what T is going to equal, and I kind of already got the cat out of the bag. Isn't T going to equal 6 in that case? Right? Time has been 6 years. So what I also ask you to do is write this down. Show me what you're punching in the calculator, because we'll let the calculator do all the work, but I can't grade your calculator. I can only grade your paper. So that's a 9. So we'll do 1.035 to the 6th power to 2025 minus 2019 is how I got that. And we'll go punch him in. 129 times 1.035, boom, to the 6th. And this should definitely be more than 129 when we punch that in, because it was growing. But let me ask you this. What label are we putting on this for teen spending? Like if we was to put a label on this, what would we put? Billions of dollars, right? I was looking for dollars, but you even said the billions of dollars part, right? So what do you think about all these decimals? Do they matter or do they not matter? Like, do you want to call it 158 billion, 159 billion, or put some decimals on that? What do you think would be the wisest decision to do? Why do you want to put decimals? It does make it more accurate, right? What if you threw that away or rounded it up, whatever, you know? Sometimes you throw it away, sometimes you round it up. But like, how much money are you throwing away right there in that case? $500 million, you know? It's like, that's a lot of money to be thrown away. So I think we'll put, let's do 3 decimal places. So about 158.574, 158.574. And then what's the label on that? $1 billion. So you put the dollar sign in front and then put the billion at the end. It doesn't tell us how to round, so I just kind of said, 3 decimal places is pretty good, you know. But on a test or something, I would tell you definitely what to round to on that one. But I don't want to throw away $500 million if I really don't want to. You know, it's like $500 million just gone. It's like, whoa, bro. So cool. Next guy, read him for the juicy word. Juicy. It's not as obvious this time as grow was before. What do you feel the juicy word is? Eliminate is the correct word. Exponential growth or exponential decay? Exponential decay. And also, just to add on to that, how we know it's decaying is eliminate, but how it's exponential is because it's eliminated by 1% every time, right? So if they're eliminating a certain percent, that's going to be exponential decay. Let's do a little A equals. The amount is going to equal. What is the starting amount of caffeine after this person has drank their cup of black tea? 35 milligrams. And then we'll do a little 1 minus 0.125, you know, because that's what has to happen in the exponential decay. You got to take 100% minus your 12.5%. Decreases. So that's an exponential decay because it's decreasing by 1%. And we'll go write our orig, general equation. They're talking about the atmospheric pressure. So originally, it's 14 pounds per square inch. Then, since we're decreasing by 20%, take 1 minus 20%. Don't you get 80%? You don't have to have the 0 if you don't want it. To the tth power, or whatever variable they want us to use. And then what's our decay factor? 0.8 or 0.80, whichever one you write is fine with me. And then the last thing, I'll let you figure that out. I'll pause, you can pause, and come back to me in a second. So we're doing the 10 miles. The 50 is kind of a funny number. We'll discuss him in a momento. So we're going to the 10th power because it's like atmospheric pressure miles above. So we'll do that 14 times the 0.8, too many parentheses, 0.8 to the 10th. Rounded to the nearest tenth, about 1.5 pounds per square inch. Interesting. First, a lot of people can do that math and not realize one bit of idea of what's going on in that problem. But this is about the atmospheric pressure. And how many of y'all ever been to Denver, Colorado before? Ever been to Denver? A lot of people in the classroom have been to Denver. You know, like baseball teams love going to Denver. Football kickers love going to Denver. You know, it's like, what's so different about Denver compared to like Hayes, America or anything? What's different in Denver than Hayes? Altitude. The mile-high city. Would you believe they are 1 mile above sea level in Denver, basically, right? So if you were at sea level, the amount of like pressure that the atmosphere puts down, like the gravity factor, every square inch of mass that you got right there, it's about 14 pounds per square inch. That's like how heavy things are. Well, when you go up just 1 mile, you know, up to Denver, that's less, you know, so things weigh less, quote unquote, weight less. You know, they have less pressure on them, so that's why baseballs travel farther, footballs travel farther in that situation. That's 1 mile. How many miles did these people go up? That's way up there, right? So for every square inch of your body that weighs 14 pounds, now it's only going to weigh 1.5 pounds in that case. So Then why is the 50 miles in there? Because this formula only holds true if you go up to 50 miles high. Once you get past that, the formula just doesn't work anymore in that case. So that's why when you hear zero gravity, you know, people are floating and all that stuff because there's no atmosphere pushing them down. So nice. All right, let us know if you have any questions. Have a good one.